When you train a large language model, the training loss mostly falls in a smooth, boring curve. The numbers drift downward day after day, and nothing seems to happen. But early on, if you look really closely, there's a strange little bump. For a brief window, the loss wiggles, almost stalls, and then drops again. Most people would never notice it. In a 2022 paper from Anthropic, Chris Olsson, Catherine Ola, Nelson Elhedge, and their colleagues zoom in on that bump and find something remarkable hiding inside it. At that exact moment, the model is teaching itself a brand new trick called in-context learning, and a specific little circuit is being born to power it. This is the story of how one tiny mechanism explains one of the biggest abilities of modern AI. First, the trick itself. In-context learning is the model's ability to get better at predicting text the more context it has already seen. Give it the start of a document and it does okay. Give it 1,000 tokens and it does much better, because it has picked up the document's names, its style, its quirks and patterns on the fly. And here's the crucial part. This happens with no weight updates at all. The network's parameters are frozen. It's not training, it's adapting in the moment purely from what's in front of it. That's what makes it feel almost like reasoning. You can see the effect in this chart. Across every model size, the loss on a token drops as that token sits later in the context. Bigger models simply start from a lower curve, but they all bend the same way. To study something, you first have to measure it, and the authors define an in-context learning score that is beautifully simple. Take the loss on the 500th token in a context, and subtract the loss on the 50th. Think about what that captures. If the model is genuinely using the context, then by token 500 it should be far more confident than it was at token 50, so that difference is large. If it ignores context, the two are about equal and the score is near zero. The beauty is that it needs no hand-picked benchmark, no special task. It's just a property of ordinary text prediction. And because it's one clean number, we can track it across an entire training run and ask what inside the model makes it rise. The hero of the story is the induction head. It's an attention head running one absurdly simple rule. It looks at the current token, searches backward through everything it has read for the last time that token appeared, sees what came right after it, and bets the same thing will happen again. In short, if A was followed by B somewhere earlier, then the next time you see A, predict B. Look at the picture. The token node showed up before, followed by struction. So when node appears again, the head reaches back, finds that earlier match, and boosts struction for the next prediction. On repeated text, this rule is almost magical. It copies the repeat perfectly, token after token, even for words it has never seen before. How does a transformer actually build that rule out of attention? Here's the elegant part. It can't be done with a single head. It needs two working together across two layers, which is exactly why one-layer models never manage the trick. The first is a previous token head. Its only job is to quietly copy each token's identity forward onto the next position, so every token now carries a little note saying what came just before me. The second head is the actual induction head. It uses that note to find every place the current token showed up before, attend to whatever followed, and boost it. One head decides where to look. The other decides what to say once you look. Two simple heads, one powerful behavior. Now back to that mysterious bump. When the authors plot how fast the loss is dropping over training, every model with more than one layer shows the same dramatic dip and rebound, right in the orange band here. Physicists have a name for a sudden reorganization like this. A phase change, like water freezing into ice. It's narrow, it happens at roughly the same point for models of wildly different sizes. And it is absolutely not random noise, because in that same tiny window, two things happen at once. Induction heads suddenly crystallize inside the network, and the in-context learning score leaps upward. The bump isn't a stumble in training. It's the precise moment the model rewires itself to learn from context. Here's another way to see the same event, and it's striking. This heat map shows how much the model improves at each position in the context as training marches on. Look at the one-layer model on the left. It basically flattens out after the 50th token, a sharp edge, and it stays that way forever. No matter how long you train it, that single-layer model never learns to use long context, because it physically can't build the two-head circuit. Now look at the models with more than one layer. They keep cutting their loss deep into long contexts, thousands of tokens in, and that whole ability switches on right at the phase change, the highlighted vertical band. Before the band, short memory. After it, the model can suddenly reach far back. To pin the timing down precisely, the team had to measure each model snapshot in a careful, repeatable way. Here's the recipe. They run every snapshot over the same set of examples. Then for each example they pull out the loss on one consistent token, building a vector of losses for that snapshot. Finally, they compress all those vectors down into a shared low-dimensional picture using principal component analysis. The payoff is that they can lay out, on a single timeline, exactly when induction heads appear and exactly when in-context learning jump. And when they do, the two curves move together so tightly, snapshot for snapshot, that it becomes very hard to believe they're unrelated. The suspect was at the scene at the exact moment of the crime. So we have a suspect, the induction head, and a phenomenon in context learning showing up at the same time. But any good scientist will tell you that co-occurrence is not proof. Two things happening together could share a hidden cause, or be pure coincidence. So to argue that induction heads actually cause in-context learning, the paper does something careful. It lays out 6 independent lines of evidence, each attacking the question from a different angle. No single one is a knockout. But stacked together, the way a courtroom case is built, they become genuinely hard to argue with. Let's walk through all 6. Argument 1 is the macroscopic co-occurrence we just hinted at. In these plots, each column is a model, and the colored lines are individual attention heads, with the induction heads picked out by color. Watch what happens in the phase change window. The induction heads light up, and at the very same time the model's in-context learning score improves dramatically, by around 10%. And here's the control that makes it convincing. The one-layer model on the far left, which simply cannot form the two-head circuit, shows no induction heads and no such jump at all. Where the mechanism is impossible, the ability never appears. That timing isn't a coincidence, it's a fingerprint. Argument 2 is coperturbation, and it's the clever one. Correlation gets a lot stronger when you can nudge the system and watch it respond. The logic is this: if induction heads really drive the effect, then deliberately changing when they form should change when in-context learning appears. So the authors modify the architecture in ways that make the two-head circuit easier or harder to assemble, pushing its formation earlier or later in training. And sure enough, the in-context learning jump slides right along the training timeline to match. Move the proposed cause, and the effect moves with it, in lockstep. That's exactly the signature you'd expect if one is genuinely driving the other. Argument 3 is the most direct test of all: ablation. This is the interpretability equivalent of a knockout experiment in biology, where you disable a gene and see what breaks. In a small model where we can identify the induction heads precisely, the researchers simply switch them off at test time, clamping their contribution to 0, and leave everything else untouched. The result is immediate and clear. The model's in-context learning ability drops substantially. The very capability we were trying to explain falls away the moment the suspected mechanism is removed. That is about as close to a clean, controlled experiment as you can get inside a neural network. Argument 4 answers the obvious objection. Surely just copying repeated text is far too simple to explain something as rich as in-context learning. But when you watch induction heads in larger models, they turn out to do far more than literal copying. Look at this real example. The head sees the word Potters for a second time, reaches back to the first mention, moves that information forward, and boosts Potters again. The same head handles Dursley a moment later in a completely different sentence, and it doesn't stop at exact repeats. These heads do soft, fuzzy pattern matching, nearest neighbor style. They complete analogies. They even help with translation between languages. The narrow copy the repeat rule grew, all on its own, into a flexible general-purpose tool. Argument 5 is mechanistic plausibility. This one is special, because in small attention-only models, we don't have to guess how the head works. We can actually read the circuit directly off the weights and verify it mathematically. In this scatter plot, each point is a head. The heads that behave like copiers in practice also carry the matching mathematical signature in their output weights, and you can see the points line up cleanly along the diagonal. Behavior and mechanism agree. And because we understand precisely how the head copies, we can also see natural, concrete ways that the very same machinery could be repurposed for more general in-context learning, instead of having to invent some brand new and unexplained story. And that leaves the honest caveat, which the authors are careful to state. The cleanest, most airtight evidence all comes from small models, where we can fully dissect the circuit. In the giant frontier models, we simply can't yet examine every head with that kind of certainty, so the case there is suggestive rather than complete. This is where argument 6, continuity, does the heavy lifting. When you measure these plots prefix matching against copying, across the whole range, from tiny models on the left up to the very largest on the right, the behaviors tied to induction heads and to in-context learning change smoothly, with no sudden break or discontinuity at any scale. And when everything scales continuously like that, the simplest, most parsimonious explanation is that the same mechanism we can see clearly in the small models is quietly at work the whole way up. So step back and look at what all of this gives us. A single, nameable circuit, just two attention heads wired across two layers, turns out to explain in-context learning, one of the headline capabilities of modern language models. That alone is a stunning result for interpretability. We found a real gear inside the machine and watched it turn. The paper also delivers a warning worth sitting with. Notice that this ability did not fade in gradually. It switched on suddenly, at a sharp phase change, almost like a light being flipped. If powerful new behaviors can appear in an instant during training, some of them helpful, some perhaps not, then for AI safety we badly need to be able to see them coming and understand them before they arrive. And that is exactly why mechanistic interpretability, this work of connecting the tiniest toy models all the way up to the frontier ones, matters so much. If we can read the gears, we have a chance of steering the machine.